Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video introduces Benford's Law to provide more practice conducting goodness of fit hypothesis testing in StatCrunch. Let's get started. So, Benford's Law is simply just, another distribution like we've seen before. So, you think about it in terms of the normal distribution, chi-square distribution, t-distribution. It's just another distribution, okay? It's a discrete distribution because the random variables are discrete values. It's called Benford's Law and not Benford's distribution because it actually describes the leading digits that many data sets have. So looking at the leading digits for numbers in a data set, they tend to conform to this distribution that's described by Benford's Law. So looking at the data that we have here, we've got probabilities for Benford's Law, and we've got observed frequencies for a sample of data. So in our sample data, we've got 69 values that start with the number 1, 40 values that start with the number 2, so on and so forth. We're asked to test the claim that the sample data fits Benford's Law at the 5% significance level. First, let's check to make sure our requirements are met because our procedure rests on certain assumptions. First, the data have been randomly selected, so check that off. The sample data consists of frequency counts for each of the different categories, so again, check again. And last but not least, we've got 271 total sample values distributed amongst 9 categories. They're not equally likely. So let's just take a look at the lowest expected frequency. That's for the final category. A 9 is expected to be the first digit of your data values 4.6% of the time. So we're going to take the total value, 271, multiply it by that probability of 4.6%, and we get 12.466. This value is greater than 5. And since all the other expected frequencies are going to be greater than the 12.466, because they have higher probabilities associated with them, then that means they're also going to be greater than 5. So it looks like we've got all of the requirements for our procedure met. What are our hypotheses? Well, think about the claim that's being made. The claim that's being made is that each of the different proportions follows Benford's Law. The null hypothesis, always a statement of equality. So we're just going to say that each of the proportions is equal to its respective probability there inside Benford's Law. The alternative hypothesis typically reflects the claim, but for goodness of fit testing, we actually have to take the complement of that. And so at least one of those probabilities is going to be different from the claimed value. There's of course a mismatch here, but that's okay. With goodness of fit tests, it's set to be a right-tailed test. Let's use StatCrunch to perform our hypothesis test. So we put the data into StatCrunch and we go through the options like we described in the previous mini lecture, and look at what we get here. We get a test statistic and a p-value. We can use either one to resolve our test. If we use the p-value, it's the value here at the end of the table, and comparing that with 5%, we see that we're greater than 5%, so we're outside the region of rejection. Therefore, we fail to reject the null hypothesis. Alternatively, we can compare our test statistic with the critical value. So the test statistic is going to be that second to last value right next door to the p-value, just as we've always seen it. We compare that with our critical value, which we get from our chi-square calculator. So we've got 9 categories, which means we've got 8 degrees of freedom at the 5% significance level. That's alpha. And so out comes our critical value of 15.5. That means that 15.5 is going to be this value right here. And that means that when we compare with our test statistic, we're going to be comparing with that value. So 11.28 puts us right here outside the region of rejection and outside the critical region. Therefore, we fail to reject the null hypothesis. So either way you go about it, you get the same conclusion. You fail to reject the null hypothesis. To interpret our results, okay, we have to look back and recall what our null hypothesis says. We have failed to reject the null hypothesis. Well, what's the null hypothesis? It says that each of those proportions for those categories are going to conform with Benford's law. Well, since we have failed to reject the null hypothesis, that means the null hypothesis could be true. And since the null hypothesis could be true, that means the proportion for each of those outcomes for each of those categories could be the same as the claimed value, which we get from Benford's law. So that means, yes, it could match up. The distributions could match up. And because normal internet traffic fits this distribution, that's what we get from our sample data, we don't have evidence to support there's anything out of the ordinary. Okay? The sample data fits what Benford's law said it should fit, so therefore we don't have any reason to suspect that anything untoward is occurring. Or in statistics parlance, we do not have sufficient evidence to support the claim that internet traffic is outside the norm. And that brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. We'll see you in the next video.